is a senior research fellow at ISA Tiruvananthapuram, and his interest meets with quantum information and foundation. And today is going to talk on certifying beyond quantumness of locally quantum no signaling theory through a quantum input bell test. So stage is yours, Samrat. You can.
Thank you. Thank you so kindly at SN Bose National Center. So 2 years I did my PhD over there. Now I moved with my PhD supervisor to SN Bose National Center. So thank you so much for giving me an opportunity. So I changed the title of my so I made it
your voice is breaking.
So it's on unentangled.
Your voice is breaking, Samrat.
Okay, just give me a second.
Okay, no problem.
Hello, is it okay now?
So no, your screen is not visible yet.
Sure. No, but is the voice that issue?
Yeah, your voice is now clear.
Oh. For that. So, and this is the what I talk about. It's in.
Could you share your screen?
Yeah. Your screen is not visible.
Hello.
Yes.
Is the screen visible now?
Not yet.
Oh, that's a big problem. Here it's showing it's oh.
Maybe you can log out and again you can enter the meeting room. That might help you.
Okay. Hello.
Yes.
So I'm not able to share the screen, saying that the host.
Okay. Let me give you the permission.
Okay.
The permission has been given to you. You can now try.
Yes. I'm so sorry for the interruption. So I'll just try to go along with it. So the title of the talk is Unentangled Quantum Interactive Verification of Post-Quantum Theories. Okay. Before I go into the talk, I just want to confirm the voice is not breaking, is it? And the screen is visible, right?
Yes. Everything is fine. One thing you can do that you can put your slide in full screen mode. That would be better.
Okay. So is this okay? Oh no. How to go into full screen? Can someone tell me?
Control L might help you.
Oh. This is okay, right?
Yes.
Yes. Okay. So the talk will be based on this work, which has been published in letters. So I would like to give a brief motivation for the talk. So we're going to look at a task. So the scenario is sort of like this: the prover who is claiming that he has the power to create beyond quantum states that are even more exotic than entangled states.
Again, your voice is breaking.
There are two parts. Oh. Oh.
Yes.
Oh, that's a big problem. I'm sorry. Hello. Is everything okay now? Are you able to see the screen?
Yeah, we are able to see the screen, and your voice is better now.
Okay. I'll try to increase the microphone.
Yes.
I'm so sorry for this. Okay. So the scenario is sort of like this: a prover, there's a prover who is claiming that he has the power to create beyond quantum states that are even more exotic than entangled states. Now the question is, can Alice and Bob, having no pre-shared entanglement, hence being less resourceful, can they verify the claim of this prover who is saying that he can prepare even beyond quantum states? Now, this is the motivation, but I know that you control N. So the question is now, can they do it? But I think you guys have the question that what is a prover? Who is a verifier? And what are even beyond quantum states? So these questions are popping up in your mind, I know. So I'll try to explain it as best as I can as we move along. So to discuss about provers and verifiers, we need to ask what are interactive proof systems, how to deal with them. So we'll first discuss about them. So in this case, you have two people. There's a prover and there's a verifier. Now the prover is untrustworthy. Whatever the claims you cannot trust. The claims of the prover you cannot trust. Suppose he's saying that I know the secret of X. Now the task is, can he convince the verifier? And the verifier already knows that the prover most of his claims are untrustworthy. So the question is how to do that. So to understand this, let me try to explain in this in the form of a game. Suppose there are two colored balls. One is a red colored one and one is a green colored one. Now, now the question is, can the prover, the prover is not colorblind, okay? So that's why he can distinguish the two balls. But the verifier in this case, this person, she is colorblind. So she cannot verify whether the two balls are actually different or not, because the two balls might be in all other aspects the same, mass, density, everything, it might be the same. So now how can the prover actually prove it to the verifier that okay, the two balls are actually different? So what the prover can do is he can actually take the two balls in his hand and he can actually give it to the verifier. What the verifier does, the verifier is colorblind, so she is computationally weaker. But what she can do is she can take the two balls in her hand, place it behind her back, and she can actually switch it, or maybe she doesn't switch it. And afterwards, she brings the balls out in her hand, in front of the prover, and she asks the prover to tell whether she has actually switched the balls or not. If the prover is able to say correctly every time whether the balls have been switched or not, then the verifier will be able to know, oh, okay, the prover was actually the claim of the prover was actually right. He actually knows whether the two balls are colored or not. This way, the verifier, even though she is colorblind, she'll be able to figure out, okay, the balls are actually different colors. So this is the scenario. So I hope you are able to understand what is a prover and what is a verifier. But the question still remains, what are beyond quantum states? We have heard about quantum states, we have heard about entanglement. So there has been so much hype. But what are now beyond quantum states? So to explain this, just imagine that there is a party Alice in a lab and she has some system in her lab. Now, if to this system she can associate some Hilbert space HA with some finite dimension DA and some measurements, which are a subset of subset of linear operators acting on the Hilbert space, we'll say that Alice's system is locally quantum. Now, okay, this is the scenario for a single party system, but there can be multiple parties, right? So what will be the scenario for that? But before going into that, we'll get to know about it from the Gleason-Bush theorem, that to every locally quantum system, we can associate some density operator. What are density operators? These are positive operators of unit trace, which act on that Hilbert space. But now the question remains, does the scenario remain the same for multipartite systems? So for multipartite systems, there are multiple Alices and there are multiple local systems, which we'll say are locally quantum systems, because to each and every locally these systems you can associate some Hilbert space and with some finite dimension, and we can perform measurements on them. Now, according to the unentangled Gleason theorem, which is we can find from this paper, we can see that to all these systems, and by the assumption that they are unentangled, we can associate it to some operator which are positive on product test, and they are Hermitian unit trace operator. Now, for short, we'll say that these are POPT states. Now, mind you, these are positive on product tests only, not positive on all effects. So this way, this will be more than the entangled ones. If I try to compare the two scenarios, for quantum systems, you will have this. For quantum systems, the state space and the effect space are exactly identical. For every entangled measurement, you can have entangled states like that. For every product state, you have product measurements like that. But for, let's say, this peculiar theory, which we call the SEP bar theory, that's why there is a SEP bar over there. This will be this pink or reddish color thing will be the state space, but will be the effect space, and this constraint part will be the effect space. If I try to give some intuitive visualization, you can see that these are the POPT states. These are the quantum states. Now we were talking about beyond quantum states. Where does beyond quantum states lie? They lie over here. And some examples of them will be some entanglement witness operators. So for example, if you consider quantum theory, you have entanglement witness operators, right? but these are not valid states because they give negative probabilities on entangled states. But when you move into this Seppard theory, which I was talking about a while ago, this Seppard theory, in this Seppard theory, even entanglement witness operators are valid states in this theory. The reason is, in Seppard theory, this entangled measurements are not there. Since entangled measurements are not there, the this state space is a bit more enlarged than the state space you get in quantum theory. So that's why you have this entanglement witness operators, which are also valid states in this theory. So now the question in the beginning was how to verify whether the prover was actually claiming, was saying the truth or not, whether he had actually prepared beyond quantum states or not. To understand this, let's revisit a common thing we already know because we are from the same field. What is the standard Bell scenario? In the standard Bell scenario, you have two parties. One is an Alice and there is a Bob who are space-like separated. They cannot communicate because they are space-like separated. Now, so there is a prover who has prepared a state WAB, let's say. Now, in this state, the prover is claiming that he's actually prepared some beyond quantum states. So in the standard Bell scenario, will the prover actually be able to convince the verifiers that he's actually claiming the truth or not? Before that, let's see what the scenario is. So in this case, you have some input X, input Y, which are classical inputs. You have some output A, output B, which are again some classical outputs. So this gives you a probability distribution, some PAB given XY. Now the question is, in the standard Bell scenario, will the prover be able to convince the verifiers that he's actually prepared some beyond quantum states? The question is no, because due to a well-known result by Barnum in this PRL paper, very showed that any bipartite space-like correlation obtained in any of the compositions is also achievable in quantum, which means I'll just try to brief it up. In the standard Bell scenario, even if the prover has prepared some beyond quantum states, whatever correlation he is able to prepare, for example, this PAB given XY, whatever correlation he is able to prepare using this POPT state, let's say, in quantum theory, Alice and Bob can prepare the exact same correlation from some quantum states and some quantum measurements. So you cannot get a distinction in the probability state space. So if you are not able to get a distinction in the probability state space, you are not able to separate the two state spaces, separate the two correlation spaces, sorry. So in this standard Bell scenario, the prover will not be able to prove the claim. But what about semi-quantum Bell scenario? This scenario is a bit different, but some of you might know or some of you might not. So this was first, I'll try to talk about it. So this was first shown by Buscemi in this, this scenario was first constructed by Buscemi in this paper. The scenario is sort of like this. And the two parties are there, Alice and Bob. They are space-like separated. But in this case, the state again, the prover has prepared. But in this case, the inputs are different. The inputs are not classical inputs. They are quantum inputs. The outputs are classical, but in this case, the inputs are quantum. That's the difference. Now we have used this Buscemi's scenario, and we have shown that okay, if you necessarily use some quantum inputs which are non-orthogonal, like the set of psi s A0 states are non-orthogonal, the set of psi t B0 states are non-orthogonal, then you can use this to our advantage. The prover can use this to his advantage. So what happens is, because of this psi s and phi t states, the probability distribution will look like this. PAB given psi s A0, phi t B0. You can calculate the proof and all these things are there in the paper. I'm just trying to motivate the situation, the problem. So what the prover will do, because of quantum inputs and quantum outputs, the verifiers will be able to actually verify, okay, the prover is, whatever he's saying is actually true. Why? Because the correlation spaces, in the correlation spaces, you will be able to draw a hyperplane. So for each and every quantum inputs, you can, for each and every POPT states, you can construct semi-quantum gains such that in the correlation spaces, there will be a distinction. You can draw a hyperplane. We have used the classic Minkowski-Hahn-Banach separation theorem because there is a separation in the correlation space in the because of the beyond quantum states and the quantum states. So this motivates us for the following results. we are able to show that for every beyond quantum state in the bipartite scenario, there will always exist a semi-quantum game, such that that game you can only win if you have some beyond quantum states. Quantum states will not help you to win the game. So if the prover is actually preparing some beyond quantum states, only then he'll be able to win the game. Because of that, the verifiers will be able to know, okay, he actually did prepare some beyond quantum states, because otherwise he'll not be able to win the game, because we have shown this analytically. But we did not stop at that, and we went into the multipartite scenario, and we also showed that for any multipartite scenario, for every beyond quantum states, there will always exist a semi-quantum game for that state, such that that semi-quantum game can only be won if the prover creates that state only, that beyond quantum state only. However, the quantum states will not help you to win the game. So in conclusion, we show that Bell experiment can be generalized to allow local quantum inputs. So basically the fact is, Barnum in his paper showed that if in the bipartite scenario, the parties create some correlations which lie out, which cannot be prepared by quantum states, then the theories must be unphysical. But the fact is, he did not consider the what would happen if the inputs were quantum, because he considered only the standard Bell scenario, not the semi-quantum Bell scenario. And that's why we have been able to say that this gives us a way to certify the beyond quantumness of locally quantum no signaling theories. And this in turn will show that for principles which are sensitive to the local quantum structure, you need to impose that the additional information principles are also sensitive to the local quantum structure as well. And obviously they'll have to be guided by the no signaling principles to isolate the quantum correlation. So I'd like to acknowledge my thanks to my colleagues and my supervisor, Dr. Manik Bani. So thank you. Any questions?
So thanks, Samrat. It was a very nice talk. So now our session is open for question. So participant can ask question or write the question in chat box.
Thank you for your talk. Could you please explain the meaning of using Gleason theorem?
Okay. I'll go back to it.
What is it and
okay.
what benefits
so
we can?
Okay. So Gleason's theorem. So for example, when we talk about quantum mechanics, we know what quantum states, quantum measurements are. But when you want to look at it from another perspective, like, okay, mathematically we want to look at it, then what would be the state space structure, the measurement structure, or what we call the effect space structure? So when you have some systems in your lab and you are able to associate some Hilbert space and some and you are able to perform all positive operator valued the measurements, then to each and every quantum system, let's say I prepare some electron in my lab, and the electron has some specific properties such that the dimension is this. I can associate it to some Hilbert space structure, and I can perform these measurements. So this physical system which I have prepared in my lab, I can map it mathematically to some operator, this density operator, which is a unit trace positive operator acting on this Hilbert space, in which I am able to express this physical system. And this is the Gleason's theorem for the single party system. But now when you have multiple parties and you have assumed that they are unentangled, there is no entanglement among them, then for this entire physical systems, you can associate one operator, one Hermitian unit trace operator, but it is positive on product test. So this physical system which you have in your lab, I can on pen and paper associate it to some operator which has some specific forms. But this is like the crux of the motivation.
Now it's clear. So in quantum mechanics, I can associate, for example, in left picture, row 1, and in the middle row 2, and then multiply by the tensor product.
Yes, you can do that.
Yeah. So in your case,
can do that, but yes, you. I'm sorry. You yes.
Yes, in your case, what will happen? I mean,
Yes,
what
yes.
is the difference
Okay.
between this matrix
Yes.
W and
Yes, yes, I'll go into that. So the fact is, when you assume quantum mechanics, when you assume that the entire, for example, all these systems that are there, let's say there are three systems, and when you assume that the entire system can be explained by quantum mechanics, then the tensor product structure that you use is the normal tensor product structure that we use for quantum mechanics. But when you use Gleason's theorem, the tensor product structure that can vary. For example, quantum mechanics is not the only physically possible theory. There are infinite theories starting from step theory in which the states are all product form, product or separable form, but the effect space can contain even entanglement witness operators. And this can be possible because the tensor product is some different tensor product structure, which we call the minimal tensor product structure. And when you go into Seppard theory, which I have been discussing till now, that is the maximal tensor product structure. And because of that, in the state space structure, you can have even entanglement witness operators, but so that negative probability does not arise, the effect space is reduced. In that effect space, you will not have entanglement measurements. In that, you will have only separable measurements. So that's why I'm saying, when you assume quantum tensor product structure, then you cannot go beyond quantum mechanics. But when you relax it a bit, when this tensor product structure, you relax it, then you can have lots of infinite theories starting from minimal tensor product structure to maximal tensor product structure, and quantum mechanics lies in between. That you can get in mathematically, it can be shown.
Now it's clear. Thank you.
Okay, thank you. It was a nice question.
So any other question from audience? So if it is not, then we end our session over here. And thanks, Samrat, for this beautiful talk.
Thank you so much. I'm so sorry for the problems that happened. This
Okay,
internet
it's
problem.
fine.
Thank you for staying with me.
So we are hoping you to have you next year.
Yes, I will definitely like to be there, and I hope we can be done physically so that I can be able to meet all the
Yes. We
excellent
will also
researchers
try
in the field.
to arrange the event offline mode.
Yes. Thank you so much for having me over here.
Thank you. So before ending, I have a short announcement that there is a tutorial session on Friday, 16 June from 6:30 p.m. and Anubhav Gandhi is going to take the tutorial session, and that's it. So participants are requested to attend the tutorial session. So okay, and our from tomorrow our session will start from 10 p.m. as usual. So thank you.